Hello, let's look at finding the area under this curve between x equals 1 and x equals 5. So we're looking at this area shaded yellow. So obviously this is not a regular shape. We don't have a formula for it. So we're first going to look at methods of estimating this area. The first is called Monte Carlo. Now in Monte Carlo, there's a lot of casinos. Monte Carlo is synonymous with chance. So what we're doing here is we're going to draw a single rectangle between x equals 1 and x equals 5, and the area of that will be our estimate. But do I draw the rectangle here, or should I draw the rectangle up here? I don't know. Now, Monte Carlo leaves that question to chance. Where we draw the rectangle will be entirely due to chance, hence the name Monte Carlo. So when we're doing this, the first step, we need to come up with some random values r between 0 and 1. So I'll come up with 6 such values. So we need random values from 0 to 1. You can use your graphics calculator to come up with these values or just make them up. So the problem is, though, we need to use the Monte Carlo method lots of random x values between 1 and 5, but all of these numbers are between 0 and 1. So we need to have a way to convert each of these into a number between 1 and 5. So what we're going to do is we're going to find an equation that maps 0 to 1 and 1 to 5. In other words, an equation, if you substitute 0, you get 1, and if you substitute 1 into that equation, you get 5. So we'll come up with a linear equation. But here it's just a bit different. R is like our x value and x is like our y value. So I know it gets a bit confusing there. So we're still going to find the gradient in the usual way. It's going to be 5 minus 1 over 1 minus 0, which gives... So when we're finding the actual equation, it's not going to be y minus y1 equals mx minus x1. It's going to be x minus x1 equals gradient 4 times r minus r1, and r1 in this case is 0. So if you rearrange this equation, you get x equals 4r plus 1. So what is this equation? It's just an equation that will allow me to take each of these values and convert it to a random number between 1 and 5. It's saying you take r, take each of these values, times it by 4 and add 1. So I'm going to do that one by one to each of these. So first value is 0.18. Times it by 4, 0.72. You add 1 and then you get 1.72. Same for the second. Times it by 4, add 1, I get 2.28, and I'll do that for the rest of the r values. So these are just random values along this line. Now what I have to do for each of these values is find the height of the function at that point. So 1.72 is around about here. So I want to find the height of the function. I want to find this y value here. I just substitute 1.72 into this function here. I'm going to take each of these one by one and substitute into this equation to get a list of 6 values that are the heights of the function. So now what I have here is 6 random values of this function between 1 and 5. So what I do is I take the mean or the average of these numbers. So you just add them up and divide by 6. So if I do that, I get 6.973. So what this is saying is the rectangle we're going to draw is going to have this width of 4 and a length of just less than 7, 6.973 recurring. So the area we're estimating here is just width times length, length being the number we just got, and that gives us about 27.9 units squared. You can see that this rectangle isn't a very good indicator of the area under the curve. The Monte Carlo in general is not a very good method, and it does take quite a lot of calculations, but it is really easy to understand. All right, let's now look at using trapeziums to estimate this area. So I'm now going to estimate this area shaded yellow using 2 trapezia. So I want to use 2 trapezia between x equals 1 and x equals 5. Now I want the heights of the trapezia to be the same. So we're going to have one that goes from 1 to 3. This is our first trapezium. Draw it up to the curve. And then we're going to have one from 3 to 5. So it's going to be this trapezium here. You can see that this trapezium is a much better estimate for the area than we got from the Monte Carlo method, but it's still not exactly accurate. Okay, so let's go and find the area of this trapezium, the area of this trapezium, and add them together. So we're going to use our formula here for area of a trapezium. So let's start with A1. So the height of A1, it doesn't look like the height, but it's actually this distance here because it's perpendicular to these two parallel lines. So the height here is just 2. So I'm going to change H to 2. Now A and B are the two parallel sides, this distance and this distance. So you can see that this length here is 4. This length here is 8. If you didn't know them, you would just substitute 1 into the function to get this length and 3 into this function to get this length. So the area of the first trapezium is just 2 over 2 times 4 plus 8, which gives 12. Now similarly, the area of the second one, its height is again 2, and the two parallel sides are once again 8 and 4. So it also has an area of 12. So our estimate for the area using the two trapeziums is simply A1 trapezium 1 plus A2 area trapezium 2 is 24 units squared. So that's a little less than what we got from the Monte Carlo method. All right, let's now look at, instead of using trapezia, we use rectangles. So we're now going to use rectangles to estimate this area in yellow. So I'm going to use 4 rectangles, but how do I draw them? I could draw them either left, right, or central. So what does that actually mean? Well, if we're using 4 left rectangles, it means that the rectangle meets this curve on the left. So the first rectangle would be this one here. It meets the curve on the left. The next rectangle will meet the curve on the left. It'll be this one. The next one, it's always meeting on the left. And then my final one always meets on the left. So basically, for 4 left rectangles, I'm just finding the area of each of these and adding them up. So for each rectangle, the width is 1. And to find the height, it's the value of the function on the left. So we've got 4 here, we've got 7, 8, and so on. Again, if you didn't know what these lengths were, you just substitute the x value into this function. So if we do that, we get 26 units squared. Let's look now at doing 4 right rectangles. So instead of meeting the function at the left, it'll meet it on the right. So the first rectangle would meet it on the right and be there. The next rectangle, they always meet on the right. Always meet on the right. So the 4 rectangles here are drawn in red. Again, each of them has a width of 1. So the first rectangle is just 1 times, now this height here is 7. The next rectangle is 1 times 8. And so on for the last 2 rectangles, 7 and 4, we get 26 units squared. So you won't always get the same answer using left and right rectangles. It just worked out here because it's symmetrical. All right, let's now do 4 central rectangles. So instead of drawing a left or right, we're going to draw one that meets the curve in the center. So the first rectangle will meet here at x is 1.5. We would draw the rectangle like this. The next rectangle would be where it meets the curve at 2.5. So it would be this rectangle here. So again, each of these rectangles I'm drawing in black, each of them has a width of 1. Now we need to find the lengths. So to do that, I'm going to need to substitute 1.5, 2.5, 3.5, and 4.5 into this equation here. So the areas would be 1 times 5.75. So I got this 5.75 by substituting 1.5 into this equation here. When I substitute 2.5 into here, I get 7.75, and then so on. I need to substitute x for 3.5, and then I need to substitute x for 4.5. So that's the combined area of the 4 rectangles. And if I put that in the calculator, I get 27 units squared. So all of these up to this point are just estimates. Rectangles, Monte Carlo, trapezium, just estimate. Now let's look at calculating the exact area. So to find the exact area under this curve between x equals 1 and x equals 5, I'm going to use integration. So what we're going to do is integrate our function negative x squared plus 6x minus 1 between the two endpoints. Lower endpoint always goes on the bottom, higher endpoint on the top. Now when you're writing out an integral, make sure you write the dx so you don't lose marks. So how do I integrate this function here? Well, this is just a polynomial. These are just powers of x. What I'm going to do is integrate term by term, and the rule we use is increase the power by 1 and divide by the new power. That's what I did here. Now, if you have a coefficient out the front, you just ignore it, you just leave it alone. That's what I did with the minus 1 here. That's also what we do when we differentiate. So for 6x, I'm going to leave the 6 alone, increase the power by 1, divide by the new power. Now, for minus 1, when we differentiate, it vanishes, but when we integrate, it doesn't. See, this is minus 1 x to the power of 0. So what I'm going to do is I'm going to leave the coefficient alone. I'm going to increase the power of x by 1 and divide by the new power. Now this notation here means we're integrating between 1 and 5. So note, you only need to write plus c when you're integrating. When it's an indefinite integral, that basically means there's no numbers there. When you're finding area under the curve, it's always going to have numbers here, and so you don't write a plus c when you integrate. So how we actually evaluate that, we substitute each of these values one by one. So we're going to start by substituting this value of 5. So all I do, everywhere I see an x, I replace it with 5. Everywhere I see an x, I replace it with 5. Everywhere I see an x, I replace it with 5. Now I'm going to substitute x equals 1. So everywhere I see an x, replace it with 1. Everywhere I see an x, replace it with 1. Now what you do with this number when we substitute 5 and this number when we substitute 1 is you subtract. So you get this answer and subtract this answer. So putting that in our calculator, we get 26.6 recurring, so about 26.7 units squared. So actually, it was the 4 central rectangles that were closest. They gave us an estimate of 27 units squared. Now that probably sounds really close, but in problems like engineering, that's not close at all, having such a gap. Even though it's only 0.3 recurring, it's a third of a square unit, but that can cause real troubles. So that's why if we were using rectangles or trapezia, we would use many more than I used in this video, and we'd get computers to do it, because even though one of the estimates was 27, it's actually not that close. All right, hope this video has helped. Best of luck with your validation, but you'll absolutely ace it. I believe in you and I'm proud of you, and keep up the good work.